At 6:47 a.m. local time on Monday, February 2nd, a magnitude 3.8 earthquake struck a short distance east of San Francisco in the town of San Ramon. While this in of itself was widely felt, it did not cause any damage, but then a mere 2 minutes later a magnitude 3.1 quake struck nearby. And then a magnitude 2, 1.3, 2, 2.5, 2.5 and more. What initially appeared to be an earthquake swarm was now ongoing, and then at 7:01 a.m. an even larger 4.2 quake struck. This also caused no damage apart from a few items falling off of shelves, but regardless was scientifically interesting. You see, the San Francisco metropolitan area is somewhat unique in the fact that it has so many lengthy and major fault lines that run through it. And at a minimum, 7 of these fault lines are deemed to have a theoretical potential chance, however small, of producing a magnitude 6.7 earthquake or larger in the next 30 years. These major fault lines that mostly or somewhat parallel the San Andreas fault line accommodate much of the regional tectonic strain that the San Andreas itself does not completely accommodate. As a result, it might be a bit surprising to learn that while the chance of the specific shown segment of the San Andreas Fault producing a magnitude 6.7 or larger earthquake by 2056 is a mere 21%, the odds of at least one of the other 6 faults producing such is a whopping 50%. And the recent earthquake swarm-like sequence at San Ramon occurred in very close proximity to the major Calaveras Fault, so that's our culprit, right? Well, not necessarily. Technically speaking, the right lateral strike slip fault quakes that occurred are notably closer to the smaller Pleasanton Fault, and yet the moment tensors indicating fault line slip direction do not completely align with those 2 known fault lines. I mean, the 3.8 quake is a decent match for the Calaveras Fault, but the 4.2 is not a match for any known fault. And, looking at the distribution of aftershocks, they largely align with the implied fault motion of the 4.2 quake about straight north to south. In fact, true earthquake swarms and earthquake sequences that have resembled swarms have repeatedly occurred along portions of the Pleasanton Fault with a similar orientation. I looked at the 10 days which experienced the most earthquakes on or near this fault, and every single one of them had higher magnitude aftershocks than would typically be expected. For any given main shock, the largest aftershock one can expect is on average 1.2 magnitudes lower than that quake. Since values are generally above or below this figure about 50% of the time, we get a chance of 2 to the 10th power or 1 in 1024 of this being purely from random chance. Something strange is causing these sequences to have a higher rate of larger magnitude aftershocks. While there could be some smaller faults between the Calaveras and Pleasanton faults that are generating these earthquakes, I want to throw out a completely wild and unproven bit of speculation. While my dataset is 100% a victim of a very small sample size, there might be a weak correlation between these earthquake swarms occurring during months with higher rainfall. Groundwater circulation can sometimes trigger lower magnitude earthquakes in specific areas, so maybe this could be one of them. Another thing to note is that of the 3 clusters where earthquake swarm and earthquake swarm-like sequences occur, the February 2nd, 2026 one occurred within the same zone that also produced a magnitude 5.8 quake in 1861. Regardless, the deemed chance of an actually potentially damaging aftershock, which I am defining as a magnitude 5.0 or larger earthquake occurring due to the aforementioned sequence in the vicinity during the next month, is deemed very low at 0.5%. This area could be warranted further study, as I too am interested as to why earthquake sequences in this zone do not seem to follow typical aftershock trends. I hope that you found this video interesting. As a final note, I would like to thank my new patron Clarence the Liar for supporting my work.